Okay, I'm going to speak about the work of a different team in our company, our segmentation team, on efficient vertebra segmentation with deep learning. This is work of Ari and Artyom and Danyan, actually from Tel Aviv. Okay, so why do we need vertebra segmentation? I think after Yechiel's lecture, we're pretty clear on that. So segmentation is a service. Basically, it's used for two tasks. The first task is actually very simple. Okay, so maybe first, what is segmentation? So basically the input is a CT scan. It can be from a good quality CT, some of the images Yechiel showed before. It can be from an interoperative CT actually, that can look pretty bad. It can look like this. So the input is a 3D volume. We have voxels. Each voxel just is measuring the density of that voxel. And what we want is a 3D model of the bones of each vertebra separately. And this is a service that is used in our navigation system for two tasks. The first one is quite simple. The client calls it bone boosting. Basically, the surgeon wants to navigate, and in some cases he will plan or navigate using the CT scan, and he wants to see it more clearly. So the scan can be very noisy, especially for very large patients. It becomes very noisy, very hard to see the bone, even though it's generally brighter than other tissues. And if we know exactly where the vertebrae are, we can just create a new visualization, that looks very similar to the CT, so it's very familiar to the users, but the bone is just emphasized, and that makes it easier to use and easier to plan the operation. And the other use for segmentation is, of course, for 2D to 3D registration, since we need each vertebra separate from the other in order to match it to the X-ray image. Of course, the segmentation should run as fast as possible. There were a few questions about that before. And we want the running time, hopefully, to be deterministic. Okay, so actually, I think it was Yechiel who spoke about the segmentation algorithm of ours about a year ago at a different meetup. And basically, we developed a very beautiful classical computer vision algorithm to perform spine segmentation. And this algorithm had a number of steps. So first, we find the spinal cord. It was sort of analyzing the whole image and understanding it. So the first step was to find the spinal canal, and maybe it's a little hard to see with the lighting, but this is the CT scan. It's a slice like this, and there's some filter to find areas that look like the spinal canal. It's sort of this dark disc with a low density, and then to find some path through this column of darkish discs that represent the spinal canal, and then another optimization process to get the spinal cord itself, using prior knowledge of the shape of this thing. Afterwards, there was a second step to find the back of this column and the front of this column. Then there was another step to get some rough segmentation of each disc and to separate the general area of each vertebra and get a plane roughly where the disc is to separate each vertebra from each other. And then afterwards, after we have a rough idea of the region of interest of each vertebra, there were some weights and some special filter used to calculate how each area looks, how much each area looks like a sheet, looks like sort of a flat surface, because the top and the bottom and the sides of the vertebra tend to look like a flat surface. And then afterwards there was a graph theory based algorithm to take all of these weights and separate the vertebra from its surroundings. As you can see, this is a fairly complex algorithm. The advantage of it is that we didn't need a big training data set. It's based on really understanding the anatomy of what we're looking at. And actually it works quite well. The disadvantage is that the running time of this algorithm on a standard PC, and of course you can buy some monster hardware and you make it a little bit faster, but the running time can be anywhere between 2 and 8 minutes, because it depends on the anatomy, and some of these steps don't take the same amount of time depending on the situation and depending on various parts of the algorithm logic. What's our strategy? Basically, the main goal was to make this faster. If we can get it to be more robust, we'll be very happy. But the main goal is to just make it simpler and make it faster. And the basic strategy is to replace all the runtime intense sections with deep learning. We need to train this deep learning method, so we have data. It's pretty labor intensive to create labeled training data for these algorithms, but luckily we already have a slow classical algorithm that does pretty well, so we can use that to create the ground truth and just fix it a little bit manually. If we have anything left that's not a neural network, we want to move everything onto the GPU. That way we can make things run much faster. The general outline of the algorithm, ignore the gray areas for now, is first we're going to do an initial segmentation at low resolution, and that takes about 20 seconds. and then the refinement to get to the higher resolution which the user needs takes an additional 10 seconds. Okay, so how do we do our initial segmentation at low resolution? Apologize again for the lighting, but you can believe me that the input is a patch of a CT scan. So the full CT scan doesn't fit in the memory of any GPU at all, and certainly not if we want to train it using lots of GPUs and do it efficiently, it doesn't fit into the memory. But even from a patch about this size, so you can see most of one of the vertebra, and there's enough information, or even a smaller patch actually, it's much smaller than what you see here. There's enough information so that by eye we can understand what we're looking at, and it should be enough information to do segmentation of that area. Then there's going to be some neural network. This is a hint, and maybe some of you are familiar with this architecture of what it's going to look like. And the output of the neural network, the output is coming out of the upper right module here, is going to be segmentation. And what we found, and this is very common in many of our deep learning projects, is that it's better to make the task of the neural network more difficult. Actually, if you teach the neural network to do a more difficult task, it's going to do better at this simple task. So really, we only care about bone. We don't really care about all the other things that are going on that I showed you in the previous classical algorithm, the spinal cord, the disc, etc. But what we found is that it's much better to actually train the neural network to segment all of these areas. So we have bone, we have boundaries, sort of the cortex of the bone, the outer surface of the bone, and we also are forcing the neural network to learn to find the discs and to find the spinal canal itself. And again, the training data is, we can generate it mostly automatically and just fix it up a little bit by hand using manual tools. So a few words about the architecture. This is a neural network architecture known as a 3D unit. It's quite common for segmentation tasks. So the basic principle of a neural network is you want to learn the features from the data itself. So what is a feature? A feature can be some filter that's picking up different features in the image. At first it can be edges or corners or certain textures, and then later on, as you get to a higher level representation, it can represent more interesting features of the image. And there's some nonlinearity, so each step here represents the convolutions, represents a bank of these filters that the system is going to learn from the training data, and some nonlinearity. And the basic feature of this architecture is what's called encoder-decoder. So we have this stream here, and what it's doing is slowly taking this image and turning it into a higher level representation. So each step here, we have a step called max pooling, which means we have our filter responses. We have some feature map. So here we'll have one filter that's showing how this image responds to horizontal edges. Another filter here, there are 64 channels in this stage, will be vertical edges or response to corners or maybe responses to different frequencies. And then what we do is we pool, say with 2 by 2, we get a smaller image, and we're slowly collecting spatial information and getting more and more contextual information. So as the stream goes further down, we're getting an encoding, we're getting a smaller image of feature maps, and at each pixel, we're getting information about sort of more interesting features. Yes, question?
Segmentation is on 3D or 2D image?
3D.
3D.
3D. Yeah, it's 3D. But it's just another. Excuse me? Yeah, so the input is 3D, but technically it doesn't make much of a difference. It's like there's another dimension in the data and another dimension in the filters. So everything is taking up much more space on the GPU, and you need to work with patches and not with the whole image, and maybe make a smaller network. But other than that, the technology is quite similar. Mm-hmm.
Who creates the feature map?
Okay, so in general, in deep learning, unlike in other algorithms, the feature maps are learned automatically. So you start out with just some random filters, typically, and then you learn it from the training data. So there's going to be some cost function that measures how well the output, which is coming out of the network all the way up here, how well the output matches the desired output, which is the segmentation map. And you have some function. The more similar the output is to your desired output, the better the value of this function is. And then at each iteration, we change all of these filters, typically, a little bit, in such a way to improve the cost function. Okay, that's the basic idea. It's a supervised learning type of system. So this stream is doing the encoding, and this stream going up here is doing the decoding. Basically, we're taking this small feature map and upsampling it and learning different filters to increase the resolution. Very typical architecture. The output, as we said, is multi-channel. And we have these skip connections. So if we just go down here and then all the way up here, we're going to lose a lot of the local information. So maybe we'll know that there's something here that looks like, I don't know, looks like a pedicle, looks like some area of a pedicle. A pedicle is a certain anatomical part of the vertebra. But it won't have any local information because the resolution is lower. So over here, we're taking these higher resolution feature maps or things that are even close to the image itself up here, and we're just copying it over to the other branch of the network. And therefore, the filters in the decoder arm are going to learn both to use the local information as well as the context that it's getting from here. Yeah?
Do you add cost functions for partial, middle part of the network, or just for the final part?
Sometimes. So some people, what they do is they say, okay, this guy should know how to generate a lower resolution segmentation. This guy should know how to generate even a rougher segmentation, and sort of forcing each part of the network to give something that's already learning the segmentation. In other cases, you can just have the output here. This is the original image resolution. And then when you compute the gradient of the cost function relative to all of these weights, then the gradient is going to propagate and run the other filters. And there are many, many bells and whistles that people add to these architectures. You could inject the input again here, downsize it, and put it in here explicitly, and all kinds of multi-scale things that in some cases are useful, in some cases don't make all that much of a difference. There's a lot of engineering going on in these architectures, and a lot of literature with people playing around with basic systems. Many times, just as a rule of thumb, a lot of the benefit you get is from understanding the data and even, doing data augmentation, generating artificial examples, understanding the results, and then changing the augmentations. Many times you get more benefit from understanding what the data you put into the system more than the exact structure of this system, as long as it's built with certain basic principles so that it will work and will converge at all. Mm-hmm.
Are you using transfer learning, or are you training from scratch?
Mm-hmm. Usually for medical data sets, it's better to train from scratch because they're so different from natural images.
So how long does it take to converge?
Many hours, depends. Yeah, many. It could be hours, could be days in some cases as well. Depends. This is a smaller detail. So the 3D unit guys found that if you use more filters here before downsizing it, then it helps because you don't have a bottleneck. So if you have the same number of filters and then you downsize here, all of a sudden you have a lot less information going on. So by learning more filters and then making the image basically 8 times smaller, you avoid the information bottleneck. That's, again, sort of an engineering detail of how to build this architecture. There's batch normalization because the numbers that naively you would get here can be very different from each other, and you want everything sort of to be at the same scale so that the optimization process and the gradient is sensitive similarly to all the weights in the system. And there's a way of doing it to normalize the inputs at each and every stage. And then we have a weighted loss. So in the original paper, basically the loss can have weights for each and every voxel. You can tell the system which voxels to put more weight on and which voxels to ignore. Originally, this was implemented in order to support sparse training data. So let's say you're too lazy, you don't have the resources to tag or to annotate all of the segmentation, you only annotate half of the slices, then you can tell the system, okay, ignore this slice, but still you feed it in at the original size so that it sees the whole input. And we're using it to emphasize the contours, as I'll show here. So one of the problems you get when you try to train in multiple classes is class imbalance. This comes up in many deep learning problems and classification problems, etc. And it can come up here as well. So we're training it for the blue to find the bone, and also for yellow. Yellow is the outer borders of the bone. There's going to be many fewer voxels of borders relative to bone. And naively, the system won't invest enough of its effort, or the gradient won't be sensitive enough to the weights that are important to separate between the different vertebra and identify these border areas. So this is an example. Again, you see how it behaves. You need to understand why it's behaving this way. and implement a specific solution for this. Yes, please.
Again, I'm going back to the motivation of the segmentation. The motivation is to assist the surgeon while doing the surgery?
Yes.
Okay, so here, for instance, there is like two tissues. One of them is bone, another one is...
Spinal canal.
Okay, so you want actually to help him to navigate to the bone and not to hit by mistake.
Yes, definitely. You definitely don't want him to hit the spinal canal, and you want him to navigate to specific areas in the bone.
Yes.
So he needs to see the 3D shape.
So my question, like the segmentation as a segmentation error. Like, for instance, some areas you're not sure that it is bone. So if by mistake you made a segmentation error, then the surgeon, because of your system, might do a mistake. So maybe it is better like to not just to do color, but to give the confidence of the
some confidence value.
So then kind of you can be
to leave it a little bit more. That's sort of the idea of that bone boosting features, that you boost the areas you think are bone a little bit.
Yes.
These architectures tend to have a more binary type of output. It depends what cost function you work with, but also for classification and also for segmentation. If you use a cost that's going to give you a sharp output, then typically it's not going to have very many intermediate values.
I see.
The edges will be pretty sharp.
And also
but also the edges in the image are pretty sharp.
No, I agree. But if a surgeon do a mistake, then he can say, no, it is not me, it is actually your system that is not... I mean, how does
who gets
it go
the blame?
With the insurance point of view?
We aren't up to the blame in the insurance part yet. No, in experiments on cadavers and such. Yeah, but these are good questions. The regulatory part of this is important. It's very different to get a classical algorithm approved, where if something fails, at least you understand, which stage of the algorithm failed. It didn't find the spinal canal. It didn't find this. It's very different to get approval for a neural network, which sort of, you just get all these numbers, and it's much harder to analyze.
Yeah, it is the same question like in automatic car, like it is machine learning based, and then if you do
it's very similar.
Who is to be blamed, So.
Yeah.
Well, the problem of explainability is pretty common in deep learning.
Explainability, yeah, it's always a problem with deep learning. Yeah, but this is a more... It's a more user interface type of question. It's also a question of what you're going to show them. Are you going to show them only this segmentation? Typically, no. You show them the CT scan, but you tweak it, you emphasize certain things, you can show an overlay of the segmentation, you do an additional validation. So like with the registration, you have the registration, but then maybe the surgeon has to touch a certain area with the tool and see if he's really touching. So he thinks he's navigating, and then he can verify it physically by touching a identified anatomical area with the tool and seeing if the tracking is really working. So there have to be in workflow based solutions for this as well. It always needs to be verified by other means. Okay, so here again we saw that the network wasn't finding the border areas well enough. And what we did is implemented a special weighting function. So we applied some filters, sort of a second derivative type of filter in different directions, sort of a classical algorithm. But we don't use this to detect the borders themselves. All we do is use this to mark suspected boundary areas and give those more weight while training the network. So we tell the network, okay, pay attention to these areas. We think maybe they're a border. We don't force it or constrain it. But we just use it to improve the training, and lo and behold, this does what you would expect it to do, and we get the bone cortex, the bone borders, with more emphasis.
What's the size of the pixel here?
Over here, good question. I don't know. Maybe it's a millimeter. I can't tell. But this algorithm is running on a downscaled version. So this might be 2 millimeters already, because again, it won't fit at the full resolution into the GPU, and it will run. It'll be too slow. So this is only running on a downscaled version. Right now, it's not feasible to do this for the whole thing in reasonable running time. So it's just the first stage. Okay, this is an example of the result. Actually, this is the lower resolution result. And this one on the side is a result on the full resolution of the CT, which I haven't told you about. So, yeah.
Sorry, I
Mhm,
asked
sure.
on the previous slide.
Mhm.
When you have the regions that
Mhm.
you want to pay more attention, how do
Mhm.
you do it? You take the loss function and there you augment it.
Yeah, so you have a loss function instead of it being just a sum over the voxels of the cross entropy versus the ground truth or whatever it is you're measuring, you do a weighted sum. And the weights are based on some rough estimation of the areas that you want to emphasize.
So
And
you
then
like detecting the edges, and then you use the detected edges to push the weights of the pixels that seem to...
Yeah, exactly. So, sorry, wrong direction. Yeah, so this is sort of a very simple-minded edge detector. It's just filtering for edges that look like this because the borders of the bone are denser than the inside of the bone. So it's just like a simple sort of a sheet detector or ridge detector. Okay, another thing we get for free, there are always going to be metal objects in the, or not always, but in some cases, put it this way, Yechiel talked about the preoperative CT. In some cases, there's also interoperative CT. It's a more expensive system and it doesn't exist in every hospital. But if there's an interoperative CT, and we still want the segmentation for various reasons, there's always going to be metal in the field. There's going to be maybe previous screws. There's going to be clamps that are used for the 3D tracking. And this metal is obviously very radio dense. It shows up as bright white, and it's going to confuse the segmentation. Plus, we want to find it for other reasons. Sometimes these objects can be used themselves for navigation. And this is actually a relatively easier task. We can just add an additional channel to the neural network and get metal segmentation as well. For this, we need to do artificial objects training because there aren't all that many examples of the metal objects, but we can simply introduce artificially some metal objects into real CT scans and train for that.
Have you tried running the network on broken bones?
So no, I usually the basic procedure here, the main operation here is not for people who have a broken spine or anything of that sort. It's for people with collapsed disc. Okay, and the purpose is to put a screw into the pedicles of two adjacent vertebra, and then you put a brace to hold them at the correct distance.
You know, some people do get their spine broken, and then some get. Well, I know one case that a vertebra has dissolved due to cancer.
Mm-hmm.
So that might be.
Yeah, I don't know if you'd want to put a screw into that one though, because it might break. Yeah, this is generally the bone itself is healthy, but the problem is with the disc. That's the basic clinical use case for the system.
Why is the metal detection an easier task because of the difference in?
Yeah, even if you do a simple threshold, usually you could find it, but it's not really good enough. You find like a piece and a piece and a piece, but you can see it even visually much even more clearly than the bone, just because it's a denser material. Okay. Okay. So the next step is we want to increase the resolution of this, again, just for technical reasons, because there's no way for it to run fast enough with the current technology, and also your patches would be very small. It wouldn't work so well because it wouldn't fit in the memory. So what we want to do, again, full segmentation at full resolution would take 8 times the amount of time, and it would be hard to fit it onto the GPU. The solution is to train another network to increase the resolution. So once we have a rough segmentation, we don't care about this whole volume. Most of the inside of the bone, we know it already. All we care about is the border regions. All we care about is to have an exact boundary and to learn that. So what we do is our input is not only, so this is an example of a pretty bad quality scan. There's a very faint edge. And let's say our input or our initial segmentation is the one on the right. And actually, we're going to use both of these as input. You would think this would be very helpful for the network. Actually, the only thing it really helps it do is to know which part is inside and which part is the outside, and to get an exact segmentation. That's the main benefit for using the rough segmentation as an initial input. How do you think we'll do this? The neural network, classical algorithm?
GANs?
No, unit. So it's the same, almost the same architecture. we've tried other things, and we're going to try other things as well. Actually, GAN is one of the things we're researching these days. But the quickest and most effective way to get a result turned out to be just to use basically the same exact technology. Here we need to do a lot of data augmentation. For instance, this coarse segmentation, it actually helps to jiggle it around a little bit. And it's the same problem. Basically, now your input is 2 channels. You want output just a high resolution channel, and you're working in patches. But you only have to run this on a relatively small fraction of the volume, because now you know where your bone is and you know where the cortex of the bone is. Mm-hmm.
Is the original high-res scan in any way helpful for the ground truth for the sharpening?
Yeah, so that is the ground truth for here. So that's where we get the ground truth from. Yeah, we run a segmentation, a slower classical segmentation, and human segmentation as well on the original CT scan, and that's where we get the ground truth. Mm-hmm. But basically it's learning sort of to detect the typical edges in this in these type of images, given that it knows more or less where to look for the edge, and maybe do some interpolation where you know the edge is gone and stuff like that. Yeah.
Would it be possible to solve the patch GPU thing if you could transfer the computation power to some kind of GPU cloud?
I wouldn't run it in the cloud if it's in an OR. It might be possible, you know, to put 10 GPUs there instead of 1 or 2. Again, there are also memory constraints of what's going to fit on the GPU. It's not only the speed; it's also the memory. But put it this way: we're going for something that'll run on a reasonable hardware, and not just tell the client, "Yeah, buy 10 computers, and we'll make some software system that will somehow coordinate it."
No, you can make your own cloud GPU service and just make them connect to it.
Yeah, you don't want them to be dependent on the internet. I think during a surgical procedure, you probably want to do that locally. We prefer, everybody sort of involved prefers this solution to like a brute force type of approach. Mm-hmm.
So just to get it clear, so you start by downgrading the resolution by a factor of 2, and then you increase it by a factor of 2?
Yeah, this whole thing is just upsampling by a factor of 2. Yeah. So the input is at the same resolution as the output, but this is just naively upscaled, right? You just replicate the image. Yeah, please.
Can't you just add it to the previous net and start with max pooling, and then add the kernels of the previous net to this net after downgrading it?
So you want to take the previous network and
start with the original, this image, high resolution image, and then do a max pooling.
From the high resolution image? Yeah, so that's basically to downsize it. Run it through the old network.
The previous conclusion kernels to this stage.
Yeah, so basically that's the first stage of what we do. That's equivalent to the low-res segmentation, right?
Yeah, but only that you add the convolution kernels of the previous net and trained on some
Yeah, so you're asking why not share the weights, and then the input would be coming from here.
Yeah.
It would be coming from the first downscaled resolution. You would lose this, right? You would lose the skip connection. Maybe you could take the image. Maybe. Yeah, maybe you can share the weights. Here, these guys are already seeing feature maps. They're not seeing an image. You can inject the image here. Yeah, maybe. It's not clear always. You can always experiment with these type of architectural questions and see, what you can squeeze more performance out of. It might be beneficial. Retraining is not that bad of a cost in our eyes, because you run it for a night or for a couple of days and you get the result. Okay, so to summarize, we have our low resolution segmentation. This takes about 20 seconds, mainly for the network. Actually, that's 20 seconds if this is on CPU, because on CPU it takes 10 seconds just to upsize it back. A very simple null operation. On GPU it's only 1 second. and the refinement is taking 10 seconds, again mainly for running the network itself on the boundary patches. And everything else is sort of technical steps on preparing the data, upscaling, downscaling, and getting everything technically to run on the same GPU without moving back and forth, the various software issues here that should be solved. This is one example of how the deep learning flow could work. So again, we downsample it. We have our small-scale multi-label unit. Then we can do basically what I told you about is a single-label refinement. Now from here, if we have the multi-labels, then you could imagine that we can start separating the vertebrae. So we have the discs, they sort of separate them, and then we want some other solution to perform the separation itself. So for the first application, just emphasizing the bones, we don't need it. We can show them the bone. To use the fast algorithm in something like what Yechiel is doing, we need to perform full vertebra separation. Again, we can do it with the classical algorithm. It uses various heuristics and knows where the discs are, so it knows where it should cut, and then it does some optimum. One of the next steps is, you can call it color refinement or per vertebra refinement, is to get all of the stages, including the separation between the vertebra, into deep learning. And that's one of the things we're working on as we speak. So how do you separate it, right? This is semantic segmentation. You get each voxel, what type of tissue it is. Is it bone? Is it disc? Sometimes maybe the discs will make a clean separation between adjacent vertebra. In other cases, it's not for sure. Maybe there can be some voxels that are touching each other. And then, again, you get into all kinds of questions of criteria for separation. One of the ways we're exploring right now that's in the literature is something called an iterative network. So the idea here is you have your same old unit for semantic segmentation, for marking each voxel. You have an output for the label and an additional output for the completeness score. So you do some regression here to get a completeness score. Completeness means if we're seeing the entire vertebra in a region of interest, then it's complete. And if we're seeing only part of it, then the score is low. And we're running the network, again, only on a specific area. And then we want to teach it to understand if it's seeing the whole vertebra right now, or if it needs to move in a certain direction to see the entire vertebra. So this is sort of combining the segmentation architecture with the regression architecture to move the region of interest. And this is like one trick to get from what's called semantic segmentation to what's called instant segmentation, but still benefit from many advantages that we have for semantic segmentation. So for semantic segmentation, basically everything is quite local. The network is learning local filters. It doesn't have to do anything global. And typically you need a lot less data to get a good result, because every patch you can think of as another example, or even every voxel in a way. Other architectures that do instant segmentation sort of out of the box, you may have heard of MASC RCNN, and other architectures tend to be much more data hungry and less suitable for medical data. Another direction we're looking at now, actually you guessed it, is called a GAN, a generative adversarial network. The basic idea of these architectures is as follows. So we have one network that's trying to perform some task, say to maybe generate images of cats or of dogs, to just make them up for nothing. Or here we have a different task. We're trying to generate segmentations. And we have another network called the Discriminator, whose job is to differentiate between the results of the first network and the real results. So if this thing is making cats, then this network has to say, is it a real cat or is it a fake cat, giving an image. In this case, this network is performing segmentations. And this network has to say, is this a real segmentation from the ground truth, or is this a quote-unquote fake segmentation generated by the segmenter? And then you train them sort of in a stepwise manner. So first you teach the discriminator. So you have labeled samples, right? Is this input generated by the generator, or is it a ground truth image? And you teach it to try to differentiate between them. And then at the next iteration, you freeze this network, and you try to teach this guy to fool the first one. So you try to teach him, first of all, to do segmentations that are still accurate segmentations. And second of all, you have what's called an adversarial loss. You give this guy a bonus whenever he fools the other guy. And then you train them one by one. And this is a nice way sometimes to enhance the results of these type of algorithms. This is sort of another thing we're experimenting right now. There are a few sort of recent works in the literature showing that this type of methodology can improve the segmentation. One way of looking at it is that the discriminator is basically learning some statistics on the segmentation. So it's not seeing the input CT itself, only this guy sees the input. What he's learning is what, it's basically learning what a vertebra looks like. It's learning to discriminate between something that's a real vertebra and something that could not be any vertebra at all. So another way of looking at GANs in general is that the discriminator is learning a prior on what the reasonable outputs could be. Yes, so maybe next year you'll hear about the GAN, or maybe not. We don't know yet. It's an area of ongoing research. We're checking ourselves every step of the way. We may abandon it in 2 weeks from now, or in 4 weeks from now we may know that it's very useful.
So the generator input is the raw image, right? The unsegmented raw
The generator input is the raw image. Yeah, if you're trying to make like draw fake rooms or fake cats or something, then you just give a random vector sometimes as your input. But there are other GANs that the generator is trying to perform a task, and it has a task loss as well as the adversarial loss.
There are many companies like Zebra or Mazor Robotics, and like, is there like a standardization in the field? Are you all doing the same? Are you collaborating? I mean, it is interesting, like for me.
More competing than collaborating, but I think people are doing similar things, sort of.
Do you have like FDA approval, like to some of
our clients, not us. Again, we're developing this module for a client. We're not selling it as our product. We have a client who's doing it, and they're doing the FDA, and we you know, they have their regulatory people, etc. They know what the requirements are, and we're the ones doing the work to help get it approved.
Can you use your techniques also, not just also for medical diagnostics, like she mentioned before, like to compare it to reference of healthy patients, and then to see.
Yeah, actually, yes. We have another project in the company. This is actually going to be our product, also based on various segmentation technologies for cancer diagnostics. So it's doing segmentation of tumors and then segmenting the tumor again in a follow-up image and comparing the size of these tumors. That's a little computer vision to do registration and know who is who. And doing various measurements for diagnostic applications.
If there will be misdiagnostics of the cancer, then the programmer will be responsible.
In most of these diagnostic applications, there are two steps. There's the research phase, where you're using it to help research some new drug and measure its effect, and then there's the clinical use. And those are two very different tiers of use. It's different what you need for research, and then the radiologist can go over them one by one and approve them, or for clinical use, which maybe it also has to be approved by radiologists, but the requirements will be much more stringent. Yeah.
So continuing to a previous question, how hard is it to transfer learning from just regular networks to things that have to do with medical applications? Is it completely worthless, or is there sometimes is it worth starting from regular networks?
So in some cases we have found it's useful, more for things that look more like natural images and less like a CT scan, which maybe you and I intuitively can understand what's there because we have a basic notion in our visual system of, you know, edges and blobs and areas, and maybe we've seen a model of a bone, but it still doesn't look anything like the images from ImageNet. In some cases, if you have very little data, you want to do a data-hungry task, and the images are pictures that somehow recall natural images, then sometimes we do use pre-training. But that's another advantage of segmentation tasks. It's easier to get a good result with less data. Okay.
Have you tried to maybe enhance your results using MRIs?
So for this application, I think MRI is going to be less accurate, and they use it less. They use CT typically. Accuracy is better. MRI is more suitable for soft tissue, for brain. Okay. Okay, I guess the last
For
question.
the segmentation,
Mhm.
the images they used, they were 2D representation of the CT? Like is
The
it
input, no, I just showed you one slice of the CT. Yeah, it wasn't the
slices are
DRR.
usually like this.
Yeah, I showed you a slice, so, but the input is a stack of slices. It's like a cube from the CT. It's just a way to look at it.
Okay.
Okay. Okay, thank you very much.
Thank you.